So guys, this is the first page of grade 10 graph theory in your textbooks. And now I'm not 100% sure what page that is. That's the one.
Also in which
No, because very few people do it.
and which textbook?
So this is the matrices and graph theory textbook. Obvious. And if you look through this textbook, they have grade 10 matrices, then after that is grade 11 matrices, with obviously, and after that is grade 12 matrices. So you have to take all the way past that, and that will get you to, I'm still paging, we're almost there. It's page, this is difficult because now it's page graph theory 1.
131, but it's 66.
Is it? Page 66. Or graph theory 1. All right, it looks like that. So you're looking for this page, please. All right, get your hand up. So guys, all we'll be able to get through today basically is to go through some terminology. And it is a bit odd, guys. It's going to take you some time to get used to this because it's completely different. We're never going to do something like this in 4, all right? Also the same with matrices, but matrices I think are more applicable to normal maths in a sense that we will still get to later on. But yeah, graph theory is something that's completely out, but yeah, we'll see. Okay, so if you want to, you can maybe copy down the things that I'm going to highlight here. If you want to do that, it is in your textbooks, which you are going to have for 3 years, right? So this book that you have in front of you now is going to be your 8th book until matric. So you can not highlight, you can underline and pencil if you want. Right? No, you're going to hand it in again.
I like to know.
No, so don't highlight it. Underline, that's fine.
Yeah.
No, not yours.
Okay.
Okay, so we are looking at this, right? If you want to write this down, the say it's going to be up to long enough for you to actually copy it down. That's going to be fine. And we need to get used to the terminology vertices and edges, not dots and lines. Okay? Vertices, I think we all are familiar with that term. That is a point, right? A vertex. If you're talking about like the vertices of a triangle, those are the 3 points that form the triangle. To connect. Okay. So the same thing here. Vertices are the points, the dots. And edges are the lines that connect those dots. Okay? They're just saying here, every edge starts and ends at a vertex. Alright, so you can't have an edge that just goes somewhere and there isn't a vertex at the end of that. So they've drawn some examples of graphs here, graph A, graph B, and graph C. Can we just look at graph A so we count how many vertices that graph has? 4, right? 1, 2, 3, 4. Okay, so I'm going to write underneath this 4 vertices. How many edges do I have? Now guys, before you say anything, this looks like a circle, right? So I think some of you might be tempted to count this as one edge, right? But actually, any line, it can be curved, it can be straight. I suppose it can be squiggly, but we don't really see that. But in this case, if it goes from one vertex to another vertex, it counts as one edge. Okay, so here we have one edge, and then that will be another edge. Okay, so even though it kind of looks like a connected shape, those are 2 edges. Okay. So we'll count them all now. We have 1, 2, 3, 4, 5, 6, 7. Okay, so we have 7 edges in this one. For graph D, how many vertices do we have? 4 again, right? Vertices, points. 1, 2, 3, 4. 4 vertices again. Gonna just hang on for 1 second. No, I knew this. Give me some credit, please. 4 vertices, no. It's fine, it's fine. Okay, and how many edges? 1, 2, 3 edges. So the same number of vertices, but obviously much less than together. And for graph C, 1, 2, 3, 4, 5, 6, 7 vertices, right? And how many edges do we have? 1, 2, 3, 4, 5, 6.
We are inquisitive children. We would like answers. Okay.
You can go do this. Okay, guys, then we have some types of graphs here, which is written underneath this. A connected graph. If I am giving you a question and I'm referencing a connected graph, you need to know what that means. Okay, so yeah, with graph theory, we can actually test you specifically on terminology. We can do like, remember I don't know where last you saw that. Maybe you get it in other subjects where you have like a table and like you must match things up.
Oh, yeah.
You can even get something like that in your next AP test. All right, where I can have connected graph and then I can have the definition somewhere down there and you must be able to match them up. So a connected graph has all vertices directly or indirectly connected to each other. I'll explain now what they mean by directly or indirectly. And graphs A and C are connected. So we are just highlighting the term connected graph here. So you have very little faith in me.
Now I'm going to get my life.
So guys, what we're actually going to end up using this for in matric, so it's going to take us a while to get this all, is like a computer system, right? So if we're thinking of the network at the school, all the computers are connected to the main network, but they're not necessarily directly connected to each other. So my computer and this is Glenda's computer maybe are not directly connected to each other, but indirectly they are, right? Because if you're following all the different, I'm reading how it works, but it's all connected to the same kind of hub in a sense, all right? So that's what they mean by directly or indirectly. So if we are looking at this last one especially, do we agree that this top vertex here, let me just make that one dark blue, is not directly connected to the bottom vertex here, right? Because there isn't an edge drawn directly from that one to that one. But if I follow other edges indirectly, these two vertices are actually connected to each other, right? Because there is a pathway between them, even though it goes through other edges. Okay, does that make sense? That's what they mean by indirectly. Okay, this one is not a connected graph because this vertex over here is not connected to that one. Okay, there's no way of going via edges from this top vertex to that one. Okay, as an example. Are you guys still with me? All right, so that's the first thing. Simple graphs, that's the next term. Simple graphs have no loops, which is what we would call this kind of thing, or multiple edges. What do they mean by multiple edges? I think what they mean there is that multiple edges connecting the same two vertices. That's what they mean there. So, yeah, I will add in here all multiple edges directly connecting. Sorry, I'm just gonna have to move the one across a bit. Just give me 1 second. Okay, there we go. So simple graphs have no loops or multiple edges that are directly connecting the same vertices. I'll explain now what that means. So guys, if we are looking at graph A and B, right, even if we just look at graph B quickly, do we see that in graph B, in the case of this kind of circular shape that we have down here, there are two edges connecting these two vertices. All right. So we will say that these two are multiple edges directly connecting the two vertices. Yeah. Yeah, connected and simple graphs are two separate. Okay, here's the same thing, right? We have that edge connecting these two vertices directly and that edge. Again, we have multiple edges connecting the same two vertices directly. Okay, it has to be directed from one straight to the other. In C, do we have that, guys? Is there any one, even if there's one place where you have two edges connecting the same two vertices, it's not classified as a simple graph. So if we just look here, between these two vertices, you see there's only one edge connected directly. And these two, there's only one edge connecting them directly. These two as well, and those two, all of them. Right, all the pairs of vertices are only directly connected by one edge. Okay, so that's classified as a So a loop is just basically, yeah, I think what they mean by loop there is, I'm just going to draw this in, but not necessarily a circle, but a kind of circular shape. So even that, what I'm drawing in there now, that would classify as a loop. But it also would satisfy the same thing that now the two edges are connected of the two vertices. What's the other
if there is no line, like, if they were separate, would they be?
No, connected means they have to all be connected.
If they weren't, if there was like.
Oh, if this was one graph and that was one.
Yeah.
Yes.
Then they would be connected. And would they, would the straight line would.
Top one would be something. Okay, guys. A tree. Now they're using a term here which we don't know what that is yet. I will explain it now. A tree is a connected graph with no circle. Let me just see if they did actually explain what a circle is all the way down.
There would be, it's bad, or.
No, it's just kind of vague to the rest of an example. So guys, if you have your textbook in front of you, if you look at the second half of this page, right, which I also will just bring up on here quickly. It does explain there what a circuit is, but we kind of also first have to read through part. Okay, so this page is not structured very well, but I'll show you now.
I don't see problem. I don't see any word.
Two vertices, if there are more than one edge connecting to the same two vertices directly. There are multiple edges directly to the same two vertices. So if you're looking at these two, there's one edge, there's the second one.
No, I get
Directly connected to the same vertex. have to be directly connected. So from one straight to the next, not indirectly like this. You can see all of these vertices are connected, but indirectly. I'll chat to you later. We need to carry on. Okay, so let's look at a path. Yes, you're obviously copying it down. So guys, I'm looking at this. Obviously, a lot of other stuff here. I'm looking at a path. Please, some of you need to stop talking. Thank you. Sorry, we have to define a path before we can define a circuit, and I will use the word circuit in the previous definition. So, sorry about that. Okay, a path is a route between two specified vertices. Okay, path. I think that makes sense. From one vertex to another one. But this is important, guys, so that no edge is used more than once. Okay, so it's a route between two specified vertices so that no edge is used more than once. Look at some examples now. Here. You're saying graph D. Oh, there is a graph. Now they're also saying not all edges of the graph need to be used. And the starting point is not usually the end point. When I see you, I just think. Now, the reason why they're stating that is because for a circuit, the starting point has to be B. So that is just why they make it that distinction. Yes. Yeah. So guys, a path, let's just go over that again and then I'll show you an example, is a route between two specified vertices, right, from one vertex to another one, so that no edge is used more than once. Not all edges of the graph need to be used. Oh, I see they left out the word to there, sadly. Need to be used, or just those need to be used. And the starting point is not usually the end point. Okay, so you can go from vertex A to vertex E, and you don't have to go back to vertex A. All right, from A to E could be a path. So what are they saying here? In graph D, a possible path from A to B. Have you guys copied down that? Those of you that are copying that down. Let's quickly look at graph D. Why did you mean it like that? I'm ready for that. Okay, can we look at an example of a path, guys? We have like 2 minutes. Graph D. No. That is graph D that they're talking about, alright? So now they're saying if you want to get a path from vertex A to vertex B, there are multiple different paths that you can take, guys. You can go from, obviously the easiest one here, they're saying, right, we can't use the same edge more than once, and we try to use all the edges, okay? It's like when you are going to your friend's house, you don't have to drive down every single street connecting the two houses, or in between the two houses, right? You kind of look for the shortest way, surely, or the one with the least traffic, putting your head on. All right, so we're going to say, you can go from A to B, and then from B to C, and then from C to D. That's classified, or that is classified, sorry, as a path from vertex A to vertex B. There would be other options, right? I'll use a different color. You can go from A to B, and then from B to E. So maybe there's something you want to see there at vertex E. And then you can go up to B, and then from there you can go down there, and then you get to B as well. Okay, so there are different paths. Now, what we are going to get to eventually is the shortest possible path, the shortest possible circuit, which we will talk about on Monday. All right, but we are going to apply this to actual real world scenarios, which is going to be quite nice. Yes, yeah, there are different circuits that we are going to probably. Okay, so no one is going to ask me, ma'am, where are we going to use this in